All right, we have one more presentation before our break, and we're just within about a minute of being on time, which is good. This is always a challenge. But our next presenter is Dr. Kenny from the Department of Geology in the College of Science. And Dr. Anderson is going to talk about his green routes to using coal, making chemical feedstocks from coal by dissolution in water. And Dr. Anderson also is the founder and chief technical officer of Thermoquatica, a startup company located in the incubator here that I'm sure he will also mention. Ken?
Thanks, Jeff. Well, thank you all for being here. In southern Illinois, I probably don't need to explain what you're looking at here. This is bituminous coal, and we have a lot of it, and it kind of has a bad rap. A lot of people will tell you coal is a four-letter word, which it is, but it's unfortunate that that's the case, because most of the problems that are associated with coal are not really associated with the fundamental nature of the material itself. They're associated with the way we use it and the problems associated with the technology that's applied to using it. And what I want to talk to you about today is some alternative ways to using coal that maybe are free of some of those kinds of problems. That's important because we have a lot of this stuff. Around the world, about 950 billion tons of proven reserves. That's about 10 times the amount of material we have as oil, for example. And the US has about a quarter of the world's supply of coal available to us. So we've got enormous amounts of this material that we have available to us. You think that being the case, that this would be a tremendously important resource for us, and in some senses it is, but if you look at how we use coal as a function of the amount of energy that we produce, coal peaked over a century ago. Literally, as the Titanic was heading to the bottom, coal was at the top. And since then, it's been going downhill. We use more coal every year than we did the year before, but we use more of everything, and as a percentage of the amount of resources that we use, coal has been steadily shrinking. What we did is we replaced coal with petroleum, and we've progressively become more and more and more dependent on petroleum. In fact, we use 19 million barrels of crude oil in the US every day. 19 million barrels a day. And we use that for a lot of different things. The obvious things are things like gasoline and kerosene and jet fuel and diesel fuel and those kinds of things that we're all familiar with. But about 7% of every barrel of crude oil is used for making other kinds of products. Most of those go into what we would typically call petrochemicals. We use petrochemicals to make thousands of different things that you use every day. Okay? You're literally wearing them right now. You're sitting on them. You're standing on them. You're holding them. You're touching them. You are quite literally right now draped in petroleum. What you're wearing and what you're touching are polymers, plastics if you prefer, in one form or another. The classic examples are things like polyesters, and I'll show you a few different examples. They're all made, or most of them anyway, are made from petroleum. Okay. Polymer is a word it's a compound word, and it simply represents something that's made from many monomers. Polymers are nothing more than chains of molecules linked together. Okay? Most of them are made from materials that have two groups on the end called functional groups that we use to hook these molecules together to make these chains. We can do this in a variety of different ways. Now, I'm not going to degenerate into a chemistry lesson here, so let's simplify this. PET plastic bottles, the little things that have a chasing arrow symbol for recycling, one in the middle, the water bottles and soda bottles and so forth that you're all familiar with, all started out life as petroleum. They're made up of chains of molecules, and the easiest way to think about this is to think about polymers as having a hook and an eye. And what clever chemists and clever engineers do is they take the hook and they put it through the eye and they link these things end to end to end to end and build up long chains of these things, and that's what PET is. It started out as petroleum, we ran it through a couple of processes, modified some of the materials that were there, and then we hooked them end to end to end and we made plastic. if you actually look at the sequence of events that goes into making that particular plastic, it starts out as crude oil. We pump that out of the ground, we put it on a tanker or in a pipeline, we send it to a refinery, we distill it, we make something called naphtha, which is one of the fractions that we distill out of crude oil. We take the naphtha, we separate a material from that called paraxylene. We take the paraxylene, we oxidize that to make terephthalic acid, and then we take the terephthalic acid and we make PET from it. This is more than a laboratory trick. This is a $30 billion a year market. Okay? This is very, very big scale business. A couple of years ago, I sat down and tried to work out the global value of the entire petrochemicals market, and I stopped when it got absurd at several $1 trillion a year. This is an enormous industry. If you look at the value chain for that particular sequence, starting with West Texas Intermediate, which is the US benchmark crude oil, you look at the price of crude oil and how it fluctuates over time, and the example here I've picked is the 2008 price spike, which we all remember. That's when gasoline hit $4.25 the first time. Okay? And you look at all the different components along that sequence, and the price of all of them tracks the price of crude oil. And the reason is because it's derived from crude oil. Okay? That's both a problem and it's a tremendous opportunity too. Because if we could find ways to make those same kinds of products, starting not with crude oil, with all its volatility and expense, but starting with other materials, that would give us a great opportunity for making these materials, breaking the tie to petroleum, and creating businesses by doing so. In fact, at $100 a barrel, and crude's been fluctuating around that during this year, that's the equivalent of about $740 a tonne for the raw material. Coal costs, depending on the grade of coal and where you are, somewhere between $10 and $80 a tonne. 10% or less of the price of petroleum. If we could start there and make these products, we'd have a tremendous business opportunity. What we did here at SIU, and what we're continuing to do in the spin-off company that we've started, Thermoquatica, is develop a process to accomplish exactly that goal. OHD, Oxidative Hydrothermal Dissolution, which is too much of a mouthful, so everyone abbreviates it to OHD, is a very simple process that we developed wherein we take solid organic materials like coal, break them down into low molecular weight materials in water using molecular oxygen. Many of the products that we produce this way have all the right characteristics to be useful for making plastics. I'm a scientist, so I have to be allowed a little bit of techno-babble, so this is it. What we do here, OHD simply works by reacting the coal in water. There's no other solvent, there's no other catalyst. It's just water and a little bit of oxygen at high temperature and pressure. What most people don't realise about water is that water is a very strange material from a chemical point of view. You're all familiar with water at room temperature. It has all the properties that you would be familiar with. You can dissolve salt or sugar in it. It doesn't dissolve oil very well. But as you increase its temperature, the properties of water change. And at 250 degrees C, or even hotter, the properties of water are much more like the properties of alcohol or even oil at room temperature. So, for example, at 250 degrees C, you can't dissolve salt in water, but you can dissolve oil in water. Okay? We take advantage of that change in properties because at the high temperatures and pressure, water behaves like a very good solvent for coal, and we introduce the oxygen, which is the reactant that breaks up the coal. All these products go straight into solution, and we can recover them as low molecular weight materials. And so does it work? Well, the proof's in the pudding, as they say. This is it. This is what we start with. Classic Illinois Basin coal. And the two flasks that are shown on my left, your right, are OHD product, what we call the liquor. The first one, the darker one, is the raw product, and it's quite concentrated. To make a point, what we did is we took a little bit of that and we diluted it with a little bit more water. And that's what you see on the far right. What that's showing you is that this product is not a colloid or a suspension or a slurry or anything with a lot of particles in it. It's a solution. These materials are broken down to low molecular weight, small molecules of exactly the same type that we use for making plastics. We started out, we've done this in a couple of different ways. The first reactor we built was a small semi-continuous reactor built in the lab. That wasn't good enough, and certainly not anything resembling anything that we could commercialise. So we adapted it and we built a continuous version of it. So that says this process can be done on a continuous basis. That's not good enough. So now we've built our process development unit. This is our first scale-up attempt. This will be installed in this building. It was supposed to be here for this week for the expo, but it's a little behind schedule on delivery. It'll be here in about a week's time, so stand by. This will carry out this process at about the 5 or 10 kilogram an hour scale, fully continuously. So what is this process? First of all, it's very simple, it's very novel, and it's very environmentally friendly. It has all the properties that we want in a process for doing a large-scale commercial operation to make the kinds of products that we currently make from petroleum, but starting not with petroleum, starting with coal. It's very easy to carry out. It doesn't involve complex or expensive or toxic catalysts or solvents or things that if they escape into the environment are problematic. It just involves the starting material, coal, water, and oxygen from the air. Get the conditions right, put those three things together in the right way, you'll break the coal down into the kinds of products that we need. It's very effective. The yields and conversions are extremely high. In fact, you can readily take this process through to 100% conversion if you so desire. And the kinds of products that we get are exactly what we need to make the kinds of materials that we need to sustain our lifestyles. And so where do you see this? Hopefully in a community near you real soon. Just a couple of acknowledgements. Our work's been supported very generously by the Illinois Clean Coal Institute and the State Office of Commerce and Economic Development through ICCI. And we've been supported by the university, particularly the Tech Transfer Office, through Jeff's office and so forth, has been very helpful with us as we've gone through the patent and IP protection process. We've also had good support from our industrial partners, particularly NIDIS and other groups that we've worked with. I have an excellent technological team led by Derek Perry, my design engineer, working with me. And we have put together quite a useful team, and I want to acknowledge the help. This has not been done by me alone. It's been a real team effort, and I appreciate everyone who's contributed. And I appreciate your attention. Thank you very much.
Time for a couple of questions.
Did I follow correctly that there is really no byproduct, nothing that would be unusable, that would be
well,
in common terms waste?
The question is about byproducts and so forth. There really aren't major byproducts. When you mine coal, you sometimes mine a little bit of rock along with it. It just goes along inherent with the material. The rocky material passes through this process unaffected, basically. So that just falls out the other end as crushed rock, usually fairly finely crushed rock. So that's not an issue, but it's really not a usable product. It's a waste. We don't make a lot of gases. We don't make much carbon dioxide, for example. There's a little bit that's produced. We make a little bit of carbon monoxide as well, but that's a useful product in its own right. So yeah, basically, there's no major issues here. We don't make NOx or SOx or other gaseous emissions that are major problems with coal combustion. They're just not. The process just doesn't go that direction.
In your scale-up, I imagine you're keeping this at pretty high pressures to keep this in a liquid form.
This is operated at high pressures, yes.
Are you having any issues with that?
No, the pressures that are needed to keep water liquid at these temperatures are high, but they're not astronomical. They're not out of the range of typical high-pressure industrial processes. So this is not something that's engineers are unfamiliar with dealing with. So yes, it's something you have to work around, something you've got to manage. It is a high-pressure process. But it's not so ridiculously high pressure that it's impractical. I'm sorry?
Is there mercury or arsenic or any other type of toxic contaminant that is involved in this at all?
we don't make mercury. I'm sorry. The question was about mercury and arsenic and some of the toxic contaminants that are associated with coal. If they're present in the coal, then they're going through the process, but they're not being emitted. There's no gaseous. There's no stack associated with this. Anything that's present that's associated with the rock stays associated with the rock. You know, the rock comes through unaffected, so it's still bound up exactly as it was when the coal was dug out of the ground. If it's associated with the organic phase, it'll end up in the water phase. That water gets recycled and stays within the process. And eventually, if levels of those things build up, then we clean up that water with conventional wastewater treatment technologies. But we don't have the kind of issues that coal combustion has, where that mercury or arsenic or whatever else is allowed to escape out a stack and therefore is sort of out of your control. We never lose control of it. It stays within the process and we can capture it and deal with it as we need to. But the level of mercury and arsenic is not problematic to the process. And it varies from coal to coal anyway. We could start with coals that are low in those materials.
One more.
I know that you like doing calculations. So have you calculated the cost of producing a plastic bottle with petroleum versus this process, especially given the high pressure and temperature?
The economics of this are to be worked out from the PDU. I've worked in industry, and it's problematic to try and estimate economics from the microscale. You just can't extrapolate from those microscale reactors. We've got to work out the energy balances, we've got to work out the processing costs, and the PDU was built to achieve that goal. So stand by 6 months.
Great. Thanks, Ken.
Sorry, I got one more.
One more question.
I'm not turning down the Vice Chancellor for research.
Ken, have you followed the process beyond just the dissolution and preparation of this sort of food product?
Into separation of the products and isolation of the individual.
And then use of the material for polymerization?
We've started to. We've certainly spent a lot of time analysing the products and the raw liquor, and we know what's in it and how it varies from feedstock to feedstock and coal to coal and so forth. We've got a lot of information about that. And we're currently involved in a couple of research projects on how you go about separating those kinds of mixtures on a lab scale and ultimately on a commercial scale to isolate the pure materials. So that's something we're investigating and working on right now.
Great.